If you listen to me in this video and you pay attention and you follow along, I guarantee you will be super good at solving these problems afterward. Statics problems are useful to find unknown forces on a structure if we know some of the other forces. So here's my 4-step framework to solving any static problem. First step, draw your free body diagram. Second step, write your equilibrium equations. So your net force is equal 0 for x and y. And 3, find your torques around a chosen axis. These steps are interchangeable and we'll see in the problems. The final step, solve for your unknowns. Before we start this video, I want you to download the cheat sheet for free in the description because I have this free framework in there. And all the formulas we'll use today are also in the cheat sheet. The problems we'll go through today will ramp up in complexity. Problem 1 is you and a buddy are trying to screw in this screw. You both have your screwdrivers on there like this. And here's the scenario. You're pushing down here with your 100 newtons of force. And you're 25 meters away from the pivot or the bolt. Your friend, who is slightly weaker, is pushing up 15 centimeters away from the bolt with a smaller force, with an unknown force. The problem is, how hard does your friend have to push to balance your forces? So to keep the two wrenches in a straight line. Because right now, if we kept pushing like this and your friend pushed with the same or less force, then the whole system would start to rotate this way. Because your friend has a shorter lever arm, so he has less torque. The question, we're looking for how much force he has to exert to balance that. Let's follow our 4-step framework, which I'll chuck in the corner really quickly. So step 1 is drawing our free body diagram, which let's go ahead and do. Let's use simple shapes for this diagram. Here's our screws and this is the bolt, aka the pivot. Let's look at the forces happening. So this distance here, 25 centimeters, and this distance here is 15 centimeters. We have 100 newtons of force pushing down on this side, which is from you. And on this side, we have a force pushing up, which is the force of your friend. This force is unknown. We'll label the right side as B and the left side as A. The labeling process is all up to you. You can label this side as P for push and this side as F for friend. It doesn't matter. Whatever lets you remember what's what. That's our free body diagram. We have the forces acting on our system. How about step 2? This is a special case. We're actually going to skip step 2. Why? There's 0 horizontal forces. So we already know there's nothing going on sideways. All of the forces happening here are vertical forces. But the thing is, finding these vertical forces wouldn't actually help us because this is a torque problem, fundamentally. The distance from the pivot is a very important part. If we just use a force equation, we wouldn't be able to find the force needed to match each other. So let's skip step 2 and skip straight to step 3, which is finding the torque. Because it's equilibrium, net torque should equal 0. The axis we will use is the bolt. And we'll use a standard sign convention, which means clockwise is negative and counterclockwise is positive. This is usually assumed. And again, this labeling process, it doesn't matter how you do it, but this is what you'll usually see 99% of the time. Because A and B torque cancel out to 0, equilibrium, then we can write that the torque of our friend, which is counterclockwise by the way, and we'll label this torque of A, should be equal to the torque of our own push, which is going down. And because torque is equal to the lever arm times the force magnitude, then our equation can be expanded into this. Force of A, which is our friend, times his lever arm equals the force of our push times our lever arm. And remember what we're looking for. We're looking for the force our friend has to exert. So let's isolate that by dividing RA onto the other side, which gives us this equation. FA equals FBRB over RA. And we're ready to solve because we know all three of these values. The force of our push is 100 newtons. Our lever arm is 25 centimeters or 0.25 meters. And his lever arm is 0.15 meters. This is roughly equal to 166.7 newtons. That's how hard he has to push if his hand's in this position to match our torque. It's nearly 70% harder than we're pushing. This is the second example we'll go through. Imagine you're on a rooftop and you have a 20-meter steel beam, 2 equal supports on both sides. And this steel beam that spans the rooftop weighs 1,800 kilos. So this block right here is 20 meters long. On top of this steel beam, we have a 10-ton solar battery. It's 4 meters away from the right side support. Find the force that each column is exerting to hold this super heavy battery in place. Let's go through our framework. So, the free body diagram, let's go ahead and draw that. We've got our steel beam and the 2 supports and our 10-ton battery. Let's look at the forces. First, let's measure out the distance. So, this is 4 meters because this is the center of our battery. And because of symmetry, this is 4 meters as well. If you remember, this total length was 20 meters. So that means this remaining distance from the edge of this battery to the left side support would be 12 meters. This force right here is how much the battery weighs. We also have the center of gravity for the steel support, which might matter later on, because we're dealing with equilibrium and stability. And the final 2 forces are the forces that our steel supports have to exert to keep this structure stable. There. Time for step 2, which is our force equations. Now, like I said, these 2 steps are interchangeable depending on context. So let's have a look at what's going on here. We have 2 unknown forces, the force of support A and the force of support B. And because this is an equilibrium, then the vertical forces have to balance out. So the total weight that's pushing down should be perfectly counteracted by these 2 support forces, which would mean that the 2 forces of the support should equal the total weight. But here's the thing, we have 2 unknowns. We cannot solve for either one of them. So let's try torque instead, because torque usually gives us a solution. Let's skip to step 3. Here's an important choice we have to make. What are we finding the torque of? The torque of support A makes the most sense. Why? Because the left support is the pivot. If you look at this like a rotation problem, this battery is trying to crush this side and rotate down this way. And the support is trying to rotate it up this way. You can look at it like that. So the left support is the pivot. And because the force at the pivot has 0 torque, then the only forces contributing to torque would be 1, the weight of the beam, which was 1,800 kilos, acting right here at the center of gravity. 2, the weight of the battery, which is 10 tons, right here. And 3, the force that our right side support is exerting. These are the only forces that can contribute to torque, since this left side support, like we said, has no torque. It's at the pivot. So if we use torque and we use these distances as lever arms, aka distances from the pivot, then we will be able to isolate this unknown right here. And once we find the force of the right side pillar, we'll be able to find the force of the left side pillar using our force equation from earlier. That's the big picture idea. The total torque should be each of these combined. And remember, that should equal to 0. The convention we'll use is this way equals negative, and this way equals positive. So any downward force is negative, and any upward force is positive. Since they cancel out, they equal 0. So it'd be the torque of our right side support minus the two torques opposing it, which are going in the opposite direction. That would be the torque of the beam weight and the torque of the battery weight. Let's quickly make some space. The torque formula is lever arm multiplied by force. So the force of B, being this, multiplied by the lever arm, which is the distance from the pivot. It's on the edge, so 20 meters. Minus, next, the torque of the beam. And the torque of the beam would be the center of gravity weight. We'll just label it with beam weight. Multiplied by that lever arm, which is 10. Because it's in the middle, so it'd be halfway here. Minus the final torque, which is the torque of the battery. And the torque being applied by the battery is the weight of the battery multiplied by the lever arm, which is 16 meters away. Since from the center of the battery to the axis, 16 meters. We can rearrange this equation like this. The torque that we want, the torque of our right side support, equals the torque of the beam and the torque of the bat added together, equals this torque plus this torque. Because all we did was we added them and we put them on the other side. And we're getting closer and closer to isolating FB, which is what we want. Now we're ready to plug in our weight values. So the weight of the beam was 1,800 times acceleration due to gravity. Because remember, we're not looking for kilograms, that's mass. We're looking for weight, which is newtons, mg. Times the lever arm, plus the same thing for the battery, which was 10,000 kilos, and the lever arm has 16. And let's isolate FB by dividing both sides by 20 meters. This is a lot of numbers, but when you solve it, the answer you get is that the force of this right side pillar is 87,220 newtons. Perfect. If you remember our original equation for force, which was Fa plus Fb equals total weight, we are able to isolate Fa because we figured out one of the unknowns using our torque equation. The total weight of the system we actually just solved. It's the weight of this steel beam plus the weight of this battery, which is something like 115,640 newtons. Of course, we did just find our FB value as 87,220 newtons. We can subtract this value from both sides. We get Fa equals 28,420 newtons. So that's the amount of force that our left side pillar is exerting. As you can see, because our super heavy battery leans toward FB, this right side support pillar has to exert more force to keep this structure stable. This next problem is a wall-mounted solar panel arm. So imagine a wall with a hinge, and this hinge has a uniform arm coming out of it. Uniform just means that the mass is distributed evenly. This metal arm is 4 meters from the wall and weighs 800 newtons. It's connected to a cable. The end of the arm to the top of the wall has a cable, and this cable is angled at 40 degrees from the horizontal. This system is in equilibrium. Let's find two values. First thing is the tension in the cable. The second thing is the X and Y components for the force that the hinge is exerting to keep this structure stable. We're going to use our reliable problem-solving framework, starting with drawing the free body diagram. It's going to look pretty similar to our sketch. We've got the wall, we've got the hinge, we've got our arm coming out, and there's the cable. This cable, we've got the force of tension. The arm right in the center has its weight. It's in the center because it's evenly distributed in terms of mass. And this weight is equal to 800 newtons. And we have the force that the hinge exerts. And each of these forces have an X and Y component happening. For this problem, again, we're going to skip step 2. we're going to look at the torque equation. Since we're solving for a tension cable, the torque equation works very well. And you'll see exactly why when we solve. What's contributing to torque? These sideways forces don't contribute to torque because they're acting along this line toward the pivot. The only things affecting torque is this weight, the y component of tension, and the y component of the hinge. The y component of the tension is Ft sine 40 because we know this inside angle is 40, and the weight of this arm acts 2 meters from the center. Here's how we find the torque around the center. The torque is equal to 0, so that's our equilibrium equation. That means our total torques in both directions balance out. So the torque coming from our tension is equal to the torque coming from our arm. If you're wondering where these numbers came out from, these are the lever arms. The tension is 4 meters away and the arm is 2 meters away. From here, we can solve for tension by dividing this value to the other side. The force of tension equals 800 times 2 divided by 4 sine 40. This is roughly 622 newtons of force. Perfect, that's eliminated one unknown. So this force right here, 622. Go back to step 2, which we skipped, which is the force equation. So this system has a vertical net force of 0 because it's balanced. Horizontally, it's also 0. So let's start with the y component. And usually in these problems, you look at both x and y. But let's start with y. Since it's 0, all of the up forces balance with the down forces. The up forces of this system is the y component of tension, which is Ft sine 40, plus the up component of the hinge. This is equal to the down component, which is the weight of the arm. The only unknown here is hinge y. Let's solve for that by subtracting both sides by Ft sine 40. Yeah, hinge y component equals 800 minus F sine 40. And in place of Ft, we can plug in 622 newtons, which we found. The y component of the hinge is roughly 400 newtons. Great, let's label that. 400 newtons coming up there. Next, we'll look at the horizontal forces equilibrium. What's the horizontal forces here? We have the x component of tension balanced with the x component of the hinge. Ft cosine 40, when you plug in 622, it's roughly 476 newtons. So that's the x component of the hinge, since it's equal. And here's our final answers that we found. The tension in the cable, 622 newtons. The hinge forces, we have the y being 400 and the x being 476 newtons. Here's our final answers. We just solved the entire problem. All we did was we applied step 2 and 3 and we solved for all of the unknowns by plugging in values that we previously found. To summarize, taking the torque around the hinge removed 2 unknowns instantly, and the hinge has to fight gravity and the sideways tension of the cable. The hinge is fighting that and counteracting it to keep our metal arm in place. Here's the final example we're going to go through. Imagine you're replacing light bulbs on a roadside billboard. It's a very tall billboard. So you're up on this billboard, and here's the little ledge that you're standing on. You have a ladder to reach the top of the billboard, angled at 53 degrees from the horizontal. The ladder weighs 120 newtons. The center of mass is the midpoint. The ground is rough, so there's friction, but the wall is smooth and there's no friction. What we're trying to find is the friction at the base of the ladder. Let's start. So, free body diagram, floor and wall. We also have our ladder. The ladder is angled at 53 degrees. Let's look at the forces. We have the normal force acting here, which is at the point of contact. We have gravity acting down here, which is 120 newtons. We've got the normal force of the wall pushing our ladder here. And we have static friction keeping our ladder in place. It's time for step 2, which is the force equations. So let's look at both x and y. First off, what are all of the horizontal forces? We've got the force of the wall and the force of static friction. So they balance each other out, they're equal. What about the vertical? We've got the normal force balancing the weight of the ladder. Time for step 3, which is finding the torque. And the torque is going to help us identify our unknown here. So if we use this point as the pivot, so the floor, then what's contributing to torque? We have the weight of the ladder, and we have the push of the wall. The force of the wall acts at the full height. And this full height, since this is a right angle triangle, we can use sine of our angle, and we get 4 meters. So the torque of the wall is the force of the wall times the lever arm, which is 4 meters. And you might be asking, why is the lever arm not 5 meters? Because the pivot's here, isn't it? Not here. Here's the thing. This force is not perpendicular. It's at an angle, see? By definition, the lever arm is the perpendicular line from the pivot to the line of action, the distance there. And that's this wall. So 4 meters. How about the torque of our ladder weight? We'll just say torque of L. We can do the same thing here. The distance from the pivot, again, it's not 2.5 meters. It's actually this distance here. Because the weight of the ladder is not acting perpendicular from the ladder. So how do we find this length here? The hypotenuse is 2.5, since that's halfway up the ladder. And this here is the adjacent. Cosine of 53 is adjacent over hypotenuse. If we multiply both sides by the hypotenuse, we get this. Adjacent is isolated. Adjacent is equal to 1.5 meters. So this small distance here is 1.5 meters. That's the lever arm for our weight. So 120 newtons times 1.5 meters, giving the torque for our weight. These values, because the net torque ends up being balanced as 0, then we can set these values equal to each other. So the force of the wall times 4 equals the torque of our ladder. Divide both sides by 4 to isolate force of the wall. And you find that the force of the wall is equal to 45 newtons. So that's how much the wall is pushing back here. The force of the wall is equal to the force of static friction. Why? Because, remember, horizontally, it's also in equilibrium. So there we go. This is 45. That's the problem solved. And it was a little tricky. The hardest part really is understanding when to use step 2 and when to use step 3. Usually, if you just use step 2 normally, you'll figure out whether or not you need to use step 3 first. I'll tell you a little secret. If you want a free worksheet for this, go download the cheat sheet in the description. I'll throw a worksheet in for you.